Physical vapor deposition is one of the methods to make a thin film. And in order to make a thin film, we need a pristine, clean surface. For instance, we have a single crystal. It doesn't matter, it might be a titanium oxide, it can be a metal, it can be a gold, doesn't matter. We have a surface and we want to make very thin film on the surface. In order to achieve that, we need the UHV system, and this UHV system is pumped by using turbomolecular pump, ion pump, or oil diffusion pump, doesn't matter. In this case, we can minimize the contamination. However, in order to obtain a very clear surface, we need sputtering and annealing cycles. Sputtering is argon sputtering is one of the most common one. We basically send the atoms, argon plus atoms, to the surface, and we can get rid of from the CO or other organic contaminations, and we can keep the surface clean for a while. However, even a UHV system has limitations for the cleanness. Since in the UHV chamber there are some other molecules, for instance hydrogen. Hydrogen is one of the source, or water. Water is another source. And maybe due to water, you can also create OH after a while. How much time? It's around 10 to the 4 seconds. So after this time, you can make a one monolayer contamination even in the UHV conditions. So you have a limited amount of time to perform thin film process. One of the easiest thin film production is physical vapor deposition. And there are a few different types of physical vapor deposition. One of them is molecular beam epitaxy. This method uses effusion cells for different sources. Another method is using magnetron sputtering. It is also a very useful method. But in this video, I mainly talk about the resistive heating and alkali metal deposition. So resistive heating is the easiest way, I think. We have a sample, for instance, we have a crystal surface which is green, and we have a source which is a metal. It can be gold, copper, palladium, platinum, doesn't matter. And we can heat the metal by using very high current, maybe 20 amps, maybe 30 amps. And heating is very effective. The reason is that we are at the UHV conditions, so there is no molecules, so you can't create a metal oxide. It is possible, of course it is possible, and I will talk about it, but most likely most of the material will be metal. For instance, you can evaporate the copper under UHV conditions. You can keep the sample very close to the source, and you can basically deposit the surface. And after a while, the sample is pretty cold if you compare with the source, then the copper gas atoms will condense on the surface, and you can create a very thin films. So this is happening in the UHV conditions. So you have a limited amount of time for the analysis, since after a while maybe CO, water, OH radicals, or the other organic contaminants will stick to the surface. But you can analyze the surface by using XPS, UPS, infrared, whatever, and you can measure the film thickness. You can learn the film growth mechanism, and also you can find out the electronic properties of this system. So these are possible. But if you want to deposit lithium, sodium, potassium, or cesium, or the 1A elements, these elements are very reactive, as you know, so they are very reactive. Therefore, you need a different method. It is very similar and easy, since there is another method called as alkali metal deposition. So these systems are like a feed-through. Basically, there's a lithium source, sodium source, potassium source, or cesium source, And when you apply the current, you can basically make a thin film like here. And you can see the examples for these two methods right now. This is our one of the UHV system, and I will just talk about the thin film part. So you can see our UHV system. There are 3 chambers. This is the first chamber, this is the second chamber, and this is the third chamber. The single crystal or the sample can go from first chamber to second chamber and second chamber to third chamber. So there is a mechanical system and we can move the sample without breaking the vacuum. If you look at the second chamber, so this is the second chamber, this is the ion pump, and you can see the sources. These are the sources. And for instance, this is a lithium source. And it is an alkali metal dispenser, and these sources are commonly used in surface science systems to deposit small amount of lithium onto single crystal under ultra-high vacuum conditions. Inside the source, there is a lithium-containing material. When a sufficiently high current passes through the dispenser heats up and lithium is released from the dispenser material. Natural lithium atoms leave the source and they condense on the single crystal surface, which form a thin lithium film. And if we want to, for instance, remove the thin film, then we can go to the first chamber and we have a argon source here. We have also quadrupole mass spectrometer. So by using the argon source, we can make argon sputtering and remove the thin film. We can also do the annealing, since we can heat the sample here, and we can completely remove the film and keep the surface very, very clean. Then if you want to make another film, then I can move the sample to the second chamber, I can make the film here, and then I can analyze it in the third chamber. In the third chamber, you can see our express source. This is the express source and hemispherical analyzer. And we have also here UPS source. And we can analyze the sample. And by the way, we can also perform the angle result X-ray photoelectron spectroscopy, since we can tilt the sample by using these knobs. I can also move the sample, and inside the chamber, so actually you can see a sample there, and I can put the sample by using this arm. So it's a beautiful system, and I think that's all.